Okay, many of you asked for this, so here it is. A video all about telephone sounds. Well, panel sounds to be specific. After I thought long and hard about doing a video like this, I decided that it would be too much to try to do all of the switching systems at once. I'd be pushing an hour, and that would be unbearable to edit. So we'll do 3 shorter videos instead. While I'm setting up our hardware, I should mention that these switches are complicated, and I've tried to do my best to talk about enough to make the video interesting while avoiding the several weeks worth of content it would take just to have a strong understanding of switching theory. So we'll do our best to make it a really fun video, and if you have any questions, I'll try to answer them in the comments. Oh yeah, and the recording hardware we're using? That's easy. It's a Western Electric 500 set that's been modified with a transformer and an audio output jack on the back. Importantly, the audio isn't coming from the acoustic coupler on the receiver, but straight from the tip and ring on the phone's internal network. With this method, we're always listening to the central office battery even when on hook. This, friends, is as close to the machine as you can get. We're sending that audio into a Tascam portable audio recorder, which is saving 48 kilohertz wave files at a 24-bit sample depth. I've post-processed the audio files in Audacity, putting a soft limiter on the dial pulses to knock them down 12 to 18 dB, while adding gain to make up for the loss, bringing the peaks back up to 0 dB. Trust me, the dial pulses are the least interesting part of the sounds, and without the limiter, your speakers would just be clipping endlessly, and you'd have to strain to hear the more interesting sounds, which are sometimes hidden down near negative 30 dB. I recommend listening to this video with headphones, or at least with good speakers with a decent frequency response. Some of the sounds are quiet, and at least one of them is too low range to be reproduced by small speakers like the kind found in laptops and cell phones. So with that out of the way, let's jump in. Let's first start by dialing a call. For now, I'll mute the switch room audio and just give you what we can hear over the telephone. Once we've played the call all the way through, we'll go back and slice it up and pay attention to all the small details. As we dial, note that there are several steps in establishing a connection between two phones. You'll see rods moving upward on the line finder and 3 other frames. This will be important for our discussion later. The first interesting thing we hear actually happens before we pick up the telephone. Because we're recording straight off the tip and ring coming from the central office, we can hear this. That is the noisy central office battery supply. Telephone central offices get their power from large banks of batteries that are continuously charged off of commercial AC power. These batteries not only allow the office to function if commercial power has an outage, they also provide a smooth, ripple-free source of power to drive the central office equipment, which all runs off this negative 48 volts DC and other voltages that are derived from it. Because the entire central office is running off this power source, you're also hearing sounds from our ringing supply and motors squeaking and introducing microphonics. If the other switches were running, you'd hear small noises from their relays operating as well. Also note that there's a high-frequency component here that would not necessarily be present in purely electromechanical offices. Because our battery supply also powers tons of electronic equipment, we're hearing a lot more high-frequency hiss than you would hear in, say, 1930. You may notice that once the phone is off hook, these sounds go away. This is because when we take the handset off the hook, the switch immediately moves us over to a quiet talk battery supply. The talk battery is passed through large filtering capacitors that ensure that no stray AC components make their way into the audio path between two subscribers. From the time we pick up the telephone to the point at which we hear dial tone is about a half second. In this period, a ton of things have already happened in the switch that we, the caller, are blissfully unaware of. The L relay that corresponds to our telephone line has operated. A line finder has been chosen and started hunting for our line on the multiple bank. The sender selector has begun hunting for an idle sender. The district selector associated with our line finder has moved its sequence switch off normal and cut us through to the sender that was just chosen to handle our call. The sender has moved its time measure switch off normal, closed its register steering circuit to the A register, and finally cut dial tone through to our line. Now, let's start dialing. Wait, did you hear that? Why did the dial tone only cut off after we were done dialing the first digit? Well, in the panel system, the dial tone is coupled to your line through a relay in the sender. The sender is the control circuit consisting of hundreds of relays responsible for giving you dial tone, registering your dialed digits, and controlling the rest of the machinery to connect the call. This particular relay in the sender acts just like a transformer, with two windings and a core. On the primary side of this relay transformer, the tone supply runs to ground through the contacts of another relay, the A register steering relay. Only when the A register is locked and the steering circuit has moved on to the B register will the induction of dial tone stop. While the AC relay is operated, you will hear dial tone. Once the AC relay breaks and we move to the B digit, dial tone goes away. Then we dial the next two digits. Okay, let's pause here. As soon as the third digit is registered, we hear this. But in that 0.3 of a second between the dial returning to normal and the selections beginning, the panel switch has just done some major stuff that we really don't hear. The first 3 digits of a U.S. phone number are known as the office code, and they represent the first point at which the panel switch needs to make a decision about how to route this call. In the panel system, and all of the common control systems that followed it, the actual location of the trunks on the trunk multiple is not directly related to the digit 722. Basically, that group of trunks, the 1 to the 722 office, could be in any arbitrary location on the multiple. And in order to route this call, we need to know where it is and what to do with it once we find it. That's the job of the decoder. In only 1/3 of a second, the sender sends a translator start signal to the decoder connector, which finds us a decoder to use. The decoder accepts the office code as input and returns a list of 6 instructions to the sender. 4 of these instructions represent the path the sender needs to take to access the trunks. The 5th is the amount of compensating resistance or line build-out it needs to add in order to achieve desirable signaling characteristics on the circuit. And the last is the type of signaling to use to communicate with the distant office we're about to connect to. Once the decoder returns that information to the sender and is informed of a successful transfer, it releases itself and awaits the next connection. I wish I could say more about the decoder because it's hugely important, both technically and historically in the development of computing machines, but that'll have to wait till its own video. Having queried the decoder for what to do next, the sender then proceeds to actually set up the connection. Now let's go back to the things we can hear. This series of sounds happens quickly, so let's divide them up into the individual machine actions that make them. The first th sound is the district sequence switch moving off normal. What you're hearing is the moving brass contact sliding over the spring that's touching it. Each sequence switch is a tiny state machine that controls the state the selector is in as it hunts over the bank to find our desired connection. Most selectors can be in any of 18 states, and the sequence switches advance as the call is set up and completed. We're moving the district selector from state 2 into state number 3. Here, we need to take another detour and talk about the layout of the panel frames, because this will play a critical role in understanding what is about to follow. The panel system has 4 main types of selector frames. One of them, the office frame, is optional, so we'll be skipping over it on this call. The other 3, district, incoming, and final, are required and must be used for connecting us to the called party. These frames, plus the sender and decoder, are the core parts of any panel call. The sender directs these rods upward one at a time in a fixed order. Each type of selector frame is divided into 5 banks. Each bank has 100 sets of terminals on it, stacked vertically like a giant but very skinny club sandwich. In front of the 5 banks are rods that carry 5 wipers on them. These wipers are called brushes. There are 30 rods per side of the frame for 60 rods per frame total. We only have to worry about our rod, though, so we can safely ignore the 59 other ones. In order to complete the call that we're dialing, the sender needs to guide these rods on the selector frames, that's district, incoming, and final, upward to their destinations. Once all of the rods and their brushes are in place, we will have a connection from our phone to the phone of our called party. Each action the sender takes to move a rod on a selector frame is known as a selection. Altogether, to complete a call, we normally need to make 7 selections. These are district brush, district group, incoming brush, incoming group, final brush, final tens, and final units. The very first selection we make is district brush. In this selection, the sender is telling the district selector which of the 5 brushes it will use in order to hunt for our group of terminals on the multiple bank. Remember that there are 5 banks on a frame, and each bank has its own brush. Even though there are 5 to choose from, we will only be using one of them to find our trunks. If we look back to what the decoder told us just a moment ago, the district brush was one of the bits of information. Knowing that, the sender will now connect to the district selector and ask it to move us up to brush number 1. The brush numbers always start from 0, so brush 1 will put us on the second bank of the frame. So we hear, and then we hear, that's actually 2 clicks. Here, let me slow that down for you. The sender, knowing it needs to select brush 1, closes a circuit to the district selector, which causes it to start moving upward. As the selector rod begins moving upward, so do the brushes attached to it. And all the way at the top of that rod, something else is moving too. At the very top, each rod also has a set of springs that move over a commutator bar. The commutator bar has these segments of conductive and non-conductive material on it. The conductive bits are connected directly to ground, so each time the wiper passes over a segment, it sends a pulse back to the sender. That's a we hear because we've passed over these first 2 segments on the commutator. Slowed down again, that's each of the clicks, although they happened fast, is the selector telling the sender, all right, I've moved up 1 step. Then, okay, another step. The sender counts these steps, and when it has counted enough, it tells the selector to stop. For our district brush selection, the sender will count 0, 1, stop. Once the selector is stopped at 1, we hear 2 more th sounds. The first sound is the sequence switch on the district frame moving into position number 4. In this position, the district selector will operate its trip magnet. The trip magnet, we don't hear it operating, but we do hear the sequence switch move, rotates another rod on the selector with a little catch on it. In just a moment, as the brush is about to move past that catch, it will hook itself onto the brush and trip it, closing the little fingers of the brush onto the terminals of the bank. The other 4 brushes on the rod? They're going to completely pass by their catches and not trip. They will stay open and not touch any of the terminals on the frame. Once the trip rod moves the little catch into place, it's about time to start the brush rod moving up again. So let's rotate that sequence switch into position number 5. That was our second thunk, by the way, and start district group selection. As we move from district brush into district group selections, we have once again closed our circuit from the sender to the district to tell it to head on upwards again. Only this time, we're going for a longer ride, because the brush now needs to hunt upward over entire groups of terminals in search of the group that our trunk belongs to. As it does that, we're going to hear 5 more clicks, 1 for each group that the selector passes over. The sender hears those clicks too, and for each one, it counts to 5. Why 5? Well, that's what the decoder told it to do when we asked it earlier. Once the district selector rod reaches the right group, the sender tells it to stop moving. It always does this in the same way, by opening the circuit to the selector, basically cutting off the power for the drive clutch. The district selector recognizes that the control loop has been opened, and we hear another as its sequence switch skips over several states and moves directly into position number 9, Selections Beyond. From here on out, until the call is fully connected, the district selector is done with its job. By moving into Selections Beyond, it has set itself up to allow the signals from the sender to pass through it, over the trunk, and onto our next frame, the incoming selector. The incoming selector is so named because that's where calls incoming to this office from another office come in. Whether the originating office is miles away or just a few feet away doesn't matter much to us. Either way, if we want to connect this call, our next step is the incoming selector. Structurally, the incoming looks just like the district frame does. So the sender starts the selection process over again. Now the last 4 digits of the phone number we're calling are 5, 6, 7, 8. We need to get ourselves to the final frame that this subscriber lives on. Each final frame holds 500 lines, so the job now is to get us to the frame handling the 5500s block. The first final frame handles lines 0000 to 0499. The second frame handles 0500 to 0999, and so on. So if we want the frame containing 5678, we need to look for frame number 12. The trunks on the incoming frame that lead to final frame number 12 are located at incoming brush 2, incoming group 3. Now I just told you that, but the sender doesn't need to be told anything. It already knows what brush and group selection it has to make because the layout of the terminals on the incoming and final frames are static. All we have to do is finish dialing the phone number so that it can figure itself out. And here we are sitting on the incoming frame, patiently waiting for some pulses from its commutator. Let's get this show on the road and dial that 5. After receiving the digit 5, the sender closes the circuit to the incoming frame, and we hear a as its sequence switch moves from position 1 to 2. That's incoming brush. Now we hear, that was fast, wasn't it? Here, let's slow that down again. That's 3 clicks for incoming brush 2. 0, 1, 2, stop. And we hear another sound as the sequence switch moves from position number 2 to position 3. Ready now for a brush trip, which we don't hear. The incoming selector rod can't start moving upwards again until we dial the next digit, 6, so let's do that now. There's the sequence switch moving again into position 4, and the incoming selector rod heading up to group 3. Now, if we're going up to the third group, how many clicks was that? If you said 4, you're right. We always start counting at 0, so that'll be 0, 1, 2, 3, stop. And the sequence switch on the incoming frame moves to position 8 for selections beyond. Now, we have our control circuit from the sender, through the district frame, through the incoming frame, and finally at the final frame. The sequence switch at the final frame moves into position 2 for final brush. We're almost done setting up this call, but before we do, we need to get the final selector to the terminals for our called party. We're sitting on the final frame that handles the 5500 to 5599 group of subscribers, and we need to get to the bank representing the 600s group. Remember, we're dialing 5, 6, 7, 8. Well, since there are 5 banks on this frame and 500 subscribers on this frame, that means there are 100 subscribers per bank. The bank numbers start at 0, and if we want the 5600s bank, that's the second one, and it's called Bank 1. The sender already knows that we dialed 5-6, so all it needs to do is direct us to final brush 1. That's 2 clicks, please. Yes, they come fast. And then the final sequence switch moves into the tripping position, and the sender waits for us to dial some more digits. Okay, so we dial a 7. That's the tens digit in 5, 6, 7, 8, and the final frame is now going up and hunting by tens. How many clicks is that to get to the 7th group of tens? And now, all there is to do is dial the last digit, which will be an 8. This is the units digit, because we want to be absolutely 100% positive that we will end up on the correct terminal. The final frame does something special. It engages its updrive clutch, but this time, it's engaged against a slower spinning roller, which causes the brush rod to go up, but at about half the speed. We are now counting not groups of terminals, but individual terminals on the frame. And if we get that wrong, we get to the wrong subscriber. So let's engage the slow updrive and count to 8 starting from 0. And there we are. We did it. We're now connected to the called party. It sure would be nice if we could let them know about that, though. I wonder if there's a way to do that. Oh yeah, let's ring their line. Okay, that big noise you heard was the selector frames cutting the sender out of the call and cutting in the talking circuit. The incoming sequence switch moves to 10 for incoming advance, which reverses battery and ground to the sender. This reversal, when it happens at this moment, is a signal to the sender that says, okay, we did it. We're officially connected to the line now, so you can let go and go help someone else. When the sender receives the incoming advance signal, it disconnects and cuts our telephone into the actual talking path for the call. The big ka-chunk sound itself is the district sequence switch moving into position 11 and physically connecting our circuit to the incoming frame. As an aside, do you hear that boom sound after each thunk? Here, listen again. You may not be able to hear it on laptop speakers. That's the driven disc of the sequence switch vibrating on the shaft of the switch, which in turn causes the switch to vibrate against the spring nest. Isn't that cool that you can hear the actual mechanical bits of the thing moving? Anyway, where were we? Oh yeah, we just need to ring the call telephone. That's the job of the incoming frame. But here's the thing. We don't want to start ringing the called party in the middle of a ring cycle. We're equipped for party lines here, and party lines have distinctive ringing. If we start in the middle of a cycle, then the wrong party might hear a ring and think it's for them when it's not. So the incoming frame needs to wait until the ringing cycle is just starting over before it will move its sequence switch and cut ringing into the circuit. That's why there's such a long delay here. If we complete the call in the middle of a ring cycle, it will wait a moment for the next cycle to begin. So we'll now pause, wait for the cycle to complete, and move into position 14 for machine ringing. Aw, heck, they hung up without even saying hello. And after all that work, too. The next sounds you hear are what happens after the calling telephone hangs up. Now, in real life, you wouldn't hear this, but we get to on this call because we're hooked into the line. You'll hear the loud think of the handset going back on hook, and then the thip sound of the sequence switch moving. This is the district sequence switch moving into position 17, down drive. Here, all of the selectors engage their down drive clutches to bring themselves back to normal. And then the last thing we hear is our telephone being cut back over to the noisy office battery, where it will remain until we lift the handset again to place another call. Wow, that was a lot, right? A call normally takes about 12 seconds to set up from start to finish, and it took us, a lot longer than that. So let's do a quick review just to piece everything back together. Before we pick up the phone, we are on noisy office battery. Once we pick up, we're attached to a sender and also moved to the quiet talk battery. The sender gives us dial tone to indicate it's ready to receive digits. We dial 722, noting that the dial tone is not removed from the line until after the A-digit register is locked in the sender. Immediately after we do that, in only 1/3 of a second, the sender asks the decoder what to do with that office code. We don't hear this on the call, even though it's very important. Instead, we just hear the sender beginning to make district selections. First, we move the district sequence switch. Then we go up 0, 1 to our district brush. Then we move the sequence switch again, engage the trip rod, and move the sequence switch again for district group. Once we've locked in our district group selections, we dial a 5 and make our incoming brush selections. Sequence switch, incoming brush, sequence switch, ready to trip. Dial a 6, and we get incoming group. Sequence switch again, and now we have the final brush as well. One more sequence switch movement on the final frame to get that trip finger ready for the upward movement of the rod. And then we dial a 7. Sequence switch moves for final 10 selections, and we count up 8 pulses to the 7th group of 10s. Finally, we dial an 8. The sequence switch moves, and we count 9 pulses to get to the 8th units terminal. After we reach the terminal on the final frame, the call is all set to go. We just need to signal back to the sender that we're ready and incoming advance. That tells the sender to go ahead and move the district sequence switch into the talking position, which cuts through the voice path between the calling and called parties. Now, we'll wait a moment for that ring cycle to line up where we want it, and There, we're ringing the phone. So that's it. That's a call from a panel office to a panel office. I want to mention that I necessarily left out a lot of detail, and if you're anything like me, the more you learn, the more questions you have. Some things we didn't even mention are: what happens if a subscriber stops dialing? What if some or all of the trunks are busy? What if a called line is busy? How does a sender and decoder work anyway? How does the motor drive work? What about calls to manual operators or crossbar offices? You get the idea. My goal here was not to explain every single thing that happens in the panel system, but to give you an idea of what happens on the ideal intra-office call. I hope you enjoyed this, and if you have any more questions, go ahead and leave them in the comments, and I'll do my best to answer them. For the next video, we can either do more panel, or change it up a bit and do number 1 crossbar. If you have a preference, let me know about that too. Thanks. Bye.